In this lab, we're going to be learning how to read a device called an encoder. An encoder is one of the two most common sensors used in building servos. An encoder comes in two pieces. One of the pieces is attached to the stator of a motor, and the other piece is attached to the rotor. On the stator piece, there are a couple of sensors. In this particular encoder, the sensors are Hall effect sensors that can detect the presence of a magnet. The rotor part has a couple of emitter devices. In this case, the emitter is a couple of magnetic poles that are positioned around the disc. Now, an encoder has usually 4 wires, though there may be more. Some encoders come with 5 or 6 wires also. What each of these wires is for, one is for power, one is for ground, and then the other 2 are for producing signal pulses, and they're usually called A and B. If you look at this particular encoder, you'll see that they are labeled on this circuit board. If I can get this to focus. Here we are. They're labeled for power, VCC, that's the synonym for VDD, ground, and then A and B pulses. Now, the way this works is we take the disc that rotates, and as this disc rotates past the Hall effect sensors, each magnetic pole creates a pulse on one of the 2 leads, A or B, as the disc rotates. Now, this encoder and many encoders are known as quadrature encoders. The reason why it's called a quadrature encoder is because there are 4 distinctly different states that can be measured. We can measure a state where the wire A is high and B is low, another state where both wires are high, a third state where B is high and A is low, and a fourth state where both wires are low. We're going to hook this up to your PSOC first of all, just so that we can see how these A and B pulses work. Take the wire that's connected to VCC and flip your PSOC over, find a pin that is VDD, and plug the red wire into VDD. Then take the black wire and plug it into ground. Now, take the green wire and we're going to connect it to the pin that is connected to the green LED on the PSOC. On my PSOC, green is pin 02. So I'm going to flip the PSOC over and I'm going to find pin 02 and I'm going to plug in the green wire to that pin. And then blue, on my PSOC, blue is pin 03. So I'll flip the PSOC over to find pin 03 and I'll plug in the blue wire to pin 03. Once you've got that, take the disc and slide it through the hole so that you can rotate the disc on this little shaft. And watch how the colors change as you rotate this disc. You should see that they rotate through a sequence where both are off. There we go, they're both off. And then if I rotate it a very small amount, green comes on by itself. Then green and blue turn on together, then blue by itself, and then back to off. If you look very closely at the top of the disc, see if I can get it to focus. The top of the disc has a little mark on it so that you can keep track of where that mark is. Try to watch as you rotate this disc and the mark moves around how many pulses you get on the LEDs in one revolution of this disc. In encoder terminology, this is known as the PPR, or pulses per revolution of the encoder. Encoders can be bought in different resolutions or numbers of pulses per revolution. Now note that this sensor is a digital sensor. This means that we cannot detect any amount of rotation of the disc. We can only detect certain rotations. For example, you should notice that as you rotate this disc, the four colors, or the four states, off, green, green-blue, and blue, occur 3 times in a single revolution. In other words, we can get 12 distinct pulses in each revolution. Since there are 360 degrees in each rotation, this means that we cannot detect the rotation of the disc any more precisely than 360 degrees divided by 12. If we take the complete number of degrees in a revolution and divide it by the number of pulses in a revolution, we get the resolution of the encoder. This encoder cannot tell us the degree of rotation any more accurately than to within 30 degrees. This is distinctly different than an analog sensor, such as a potentiometer. A potentiometer could tell us very accurately the angle of rotation, whereas a 12 pulse per revolution encoder could only tell us the rotation angle to within 30 degrees. Now, let's take a look at how we can use PSOC to count up and keep track of the angle of rotation. Create a new project. Make sure you select the correct device, empty schematic, and if you have the option, create a new workspace. The Quadrature Encoder is not an analog sensor like the potentiometer, so we don't need to get the A to D converter like we did in that lab. Rather, open up the digital menu and then look in the functions menu. Find the item called Quadrature Decoder and drag one to the screen. You'll see that there are elements of this that are similar to a pulse width modulation signal that we've used previously. For example, we need to have a clock input. The reason why this is similar to a PWM is because a PWM is a digital kind of output, whereas an encoder is a digital kind of input. Open up the System menu and scroll down to find the clock. Drag a clock to the screen and wire it to the clock input. Now you'll see that there are 3 other inputs: Quadrature A, Quadrature B, and Index. A and B we already know about. Those are the 2 leads on our encoder that produce the pulses. Index is a 3rd possible input that some encoders have. This is a wire that pulses just one time every time the encoder makes a full revolution. Our encoders do not have this wire. Double-click on the Quadrature decoder and click on the tab that says Use Index Input. Uncheck the box that says Use Index Input and then click OK. That will get rid of the index input that we don't have with our encoders. Now open up the menu called Ports and Pins. Get a digital input pin and drag one of these pins and connect it to each of the inputs on your quadrature decoder. These are going to be the two pins that we have plugged in A and B to on our PSOC. Double-click on the CYDWR window. On my encoder, I plugged A into pin 03 and I plugged the B wire into pin 02. Check on your encoder in order to set the correct pin number to the correct pin on your PSOC. In other words, back in your top design window, check to see which pin you wired to A and which pin you wired to B. Then, check on your actual encoder to see which wire you wired to which pin on the PSOC, and set the pins accordingly. Next, go to the main.c. I'm going to delete these comments in the beginning, and I'm going to delete these comments here, but I am not going to delete the line that says CY global int enable. This is the line that enables the global interrupts. We have not used interrupts previously in this class, but now we do need to use interrupts. An interrupt is a piece of code that executes whenever a particular event occurs on the PSOC. In order to keep track of the rotational angle with an encoder, we need to use interrupts. We want the PSOC to increment a counter every time it receives a pulse on either the A or the B line. We can use interrupts to do this, so we need to leave the interrupt enable line in the code. The next thing we need to do is start the quadrature decoder block that we've placed. I'm going to go to the top design window and make note of what this block is called, Quad Dec 1. Then in main.c, I'm going to add a line of code that says Quad Dec 1 start with open and close parentheses and a semicolon. Next, I'm going to create an 8-bit integer called count. I'm going to use this integer to store the number of pulses that are received from my encoder. Now, in the for loop, we're going to set the variable count equal to the quad dec 1 get counter. This is a function that automatically uses interrupts to keep track of the number of pulses that have come from the A and B wires from the encoder. Next, I'd like to have some kind of an output to keep track of how many counts have been received. In order to do this, go back to the top design window and get a digital output pin. I'm going to change the name of this pin to red. Then I'll go into digital logic and get a logic low and wire it to my red pin. In the CYDWR window, I'll set the red pin to 1,6. That is the red LED on the PSOC. Now, if the count value is greater than 10, I want to turn on the red LED. So I'm going to write the value 1 to the red pin. Else, that is, if count is not greater than 10, we will write the value of 0 to the red LED. Now there's one more thing that we have to do before we build our project. Go back to the top design window and double-click on the Quad Dec 1. In the Glitch Filtering tab, uncheck Enable Glitch Filtering. Glitch filtering is a function that PSOC can apply to the Quadrature decoder in order to make it less noisy, but it takes up a lot of resources. So we're going to disable it in order that our program can all fit on the PSOC chip. Secondly, go to the counter resolution. Here we can select how many pulses we want to capture. If we set this to 1x, this will capture only one count for every 4 pulses from the encoder. If we set it to 2x, we will increment the count by 1 for every 2 pulses. And if we set it to 4, we will count each pulse as its own count. Use 4 for now, and we'll try other numbers later. Click OK, and then build your project. And if you have no errors, program the PSOC. Once your PSOC is programmed, try slowly rotating the disk of the encoder. It should be that when you go through 10 pulses, that is almost 1 revolution, the red LED comes on. When you rotate the dial in the other direction, the red LED should go back off because the count has gone below 10. If this is working for you, try to go back into the settings of Quad Deck and try changing the counter resolution. Set it to 2 or 1 and check to see how the behavior of your Quadrature decoder is different. Remember that each time you change this, you have to click OK and then program the PSOC. Once this is working for you, answer the questions in the lab for today.